Good afternoon, people of C++ and C. Thank you very much for the opportunity to victimize you today. What we're going to be talking about is supposedly about how to get the benefits of Rust traits for runtime polymorphism in C++. This is a presentation targeted towards the intermediate and expert side of the audience, but it still remains if you want to know more about this topic and you might not feel that you're picking up on everything. What I usually do, this is not an exception, is that my slides are primarily for revisiting the topics. I am not reading the slides, but they contain a lot of things that I don't say, so that you can go back to them in the video and rereading of the slide deck. There is a continuation of presentations, and you're going to see overlap between prior presentations and successive presentations. All right. So I am Eduardo Madrid, and the thing that to start with is first introducing who are we, where we are coming from, and then talking about where we're going to, because it's relevant to this presentation in particular. I am an author of open source libraries. In particular, I have communicated with this community about our work on the SWAR libraries, SIMD within a register. That is a work that is ongoing. It's very promising, the results that we are getting. My collaborators and I, we have not published the latest things that we have been doing, but they continue to be interesting and productive and encouraging. And very importantly, I authored type erasure framework that we're going to use later today for the purposes that the profile, I come from being a team and a tech lead at several companies. The type erasure library, for example, is used by the company of Snap in its flagship product of Snapchat. I carry experience from before on automated and high-frequency trading because I have always been very interested in performance and reducing latencies and hard technical challenges. And well, this is, as everything else, something that attempts to see how we use C++ to maximize the leverage between the effort that we put into whatever we do and the objective results that we get in terms of performance or anything that we want. So this presentation is on a very long line of a very long running sequence of presentations. To note, all of them are resources for you to learn more on any aspect that I'm going to be talking to you today or in the future even. But it is particularly important, for example, at C++ Now in 2021, that I collaborated with our own Phil Nash to the presentation Polymorphism a la carte, which is how to replicate something called runtime polymorphism of other programming languages. We made an emphasis on Objective-C on that occasion. Fedor Picus can tell you the importance and the big improvements that you can get by doing type erasure from the perspective of performance in a proper way. Fedor had the courtesy of quoting my work. He showed how several performance techniques that I used in type erasure he deemed to be very important. And he explained them real well. So that is another resource that you can use to understand this from the perspective of performance. And I have kept working on that C++ Online, C++ Now this year, etc. So I don't want to define type erasure beyond simply telling you that it is like a master key to implement relations of runtime polymorphism in a practical way. And this is something in which we use features of C++ that are very hardcore, that make it relevant whether you're going to be using things like, for example, the mechanism of inheritance and virtual in the C++ language itself. So this is like we use some features of C++ to make irrelevant many features of C++, literally, which is quite interesting, I believe. Okay, and this thing of type erasure that I will articulate a little better when is more relevant is what allows us to do the heavy lifting for getting real close to runtime polymorphism in the style of Ross traits. The status is that we just did at C++ now runtime polymorphism with freedom and performance, which was a theoretically oriented presentation in which we treat the subject as a design pattern, and we make an emphasis in performance in that presentation. Hopefully, a presentation that would be like the natural successor of this one, Ross traits in the style for C++, is going to be approved by the CPPCon committee. At that point, we would assume that we already have implemented the library that presents support for Ross traits. So where are we? This is the only opportunity to talk about how to go from type erasure to Ross traits, and that's what we cover in this session today. There is a little bit of a conflict of interest that I am embarrassed to continue to use my framework as the basis for these things. The reasons are multiple, but let's say that I'm just going to say that my framework is just a proof, material proof that what I am saying is possible, because with this framework it is rendered viable and possible. And I am very happy because the subject matter of how to go from type erasure to Ross traits was not going to happen as a presentation, because I wasn't going to make a proposal to yet again sell the SU libraries. But because of the circumstances of this conference, the opportunity arose, and I'm very happy to have had it. And I hope that you like the possibilities and the material that I come to share with you. Yeah, so getting into the subject matter, okay? The issue of what we're going to be doing is actually quite simple, profound and consequential, but in general quite simple. The issue is to identify the essentials of what we're dealing with so that we don't have to be bogged down with the irrelevant details. So this is a facet of what we do as software engineers quite often, of focusing on abstraction. And the reason for why this is important is that most programming languages only have the facility of subclassing to represent the subtyping relations that I'm going to be telling you about. Has the primary tool to represent abstraction. But I think I'm getting ahead a little bit. So what is runtime polymorphism in essence? It is in the title, and I have not defined it yet, right? So when you're writing the code at compilation time, that's when we normally refer to as compilation time, or the time of programming ends when we actually ask the compiler to compile, right? At that point in time, then everything is runtime. When we want it so that we don't know the actual times the application will be using, that's why it is called runtime. But we're going to focus only on their essential properties, the abstraction that I told you a moment ago. So we want to be working with the essentials in our code. When the details are resolved at runtime, then that invokes a concept of dynamic dispatch that we will revisit when we bind our implementation of runtime polymorphism, what the mechanism for the dynamic dispatch, and how to integrate them into the rest of the framework. John Lakos told me something that is quite insightful, which is that the whole idea of polymorphism, runtime polymorphism, is that you have things that when you're writing the program are of the same type, but their behavior is configured so that at runtime, different behaviors are activated. And we had to introduce the concept of a subtype. And for that, I'm going to use the idea of a rotary phone and a smartphone to tell you that if you care about the essential characteristics of a telephone, that's the example, you care about something that is able to place and receive calls, right? And very little else, because if something is able to place calls and receive calls, then it is a telephone, and you can use it whenever you want to to use a telephone. However, you obviously see that a rotary telephone and a smartphone are very, very dissimilar kind of things, okay? But we can make programs that only require the essentials of a telephone, and therefore they would work just fine whether the actual object that is managed by the code at runtime is a rotary telephone or a smartphone. So the idea that I just told you about, that you can use either, for example, a rotary phone or one of those keypad phones, a wired phone, a wireless phone. Those things mean that you can substitute and things will continue to work. That is the essence of the property of substitutability. When you have that property of substitutability, that is induced by a relation of subtyping, and the relation of subtyping, of course, has two directions. The direction of a more concrete, less abstract subtype, and less concrete, more abstract supertype. Okay, in this case, a smartphone would be a subtype, and the supertype would be the concept of the telephone. When you use inheritance, like in many programming languages, obviously the natural mapping is that we're going to represent the relation of subtyping by using base classes for the supertypes and using derived types or derived classes for the subtypes. I want you to observe that inheritance is a syntactical and structural relation. And if you want to know the solid principles that have an L in the middle, solid, you know the solid principles, who knows, have heard that? Yes. Please keep the hand up if you know what the Liskov substitution principle is. Yes, much fewer hands continue raised. The Liskov substitution principle is that when the subclassing relation satisfies the semantic relation of subtyping, okay? When making the substitutions of a derived type will not break the program. And the Liskov substitution principle means a principle that is respected when the semantics of substitutability is preserved in the way that you represented subtyping, in particular subclassing, so the derived classes can be substituted by the supertype or the base class, and things will continue to work. However, one thing that is not familiar to most programmers is that subtyping is not about inheritance. Inheritance is just one choice. Subclassing, inheritance and subclassing are synonyms for this presentation. It's just one choice about how to represent subtyping. What we want is subtyping, not inheritance, because inheritance is problematic. We will see a little bit of that in a moment. One example in a major programming language in which subtyping tends not to be related to inheritance is precisely the Ross traits. I will show you Ross traits if you don't know about them, so don't worry about that. It's just an example of subtyping implemented or represented in code without the need for inheritance or subclassing. A really great thing about C++ is it has fantastic mechanisms for compile time polymorphism, because we can have subtyping at compilation time, and we use it pervasively. Like, for example, containers, okay? You can understand the word of a container, and you can have an algorithm that does, for example, quicksort. And if in the standard library quicksort, if your container has such a thing of random access iteration, then you can use, no matter what container, the quicksort algorithm from the standard library will be able to sort it for you, right? So you can substitute anything that has the property of being random access, and quicksort will give you things sorted. That is an example of subtyping that doesn't require inheritance, because, you know, like, for example, a double-ended queue and a vector don't have an inheritance relation between them, right? You know that, right? So I was anticipating a moment ago that the problem is that we are not familiar about representing subtyping without subclassing, because that is the primary tool and probably the only tool that most programming languages give us, okay? So what is the problem? That subtyping has subclassing is actually the worst way for doing subtyping. Is in the audience people that went to Nikolai Yosuti's earlier today? There are a few hands. A quick question. Did he refer to the problems of inheritance in his presentation? I see that he referred a little bit to those problems. All right. Well, that's very important because one major difference between Ross traits and normal inheritance in most programming languages, including C++, is that it completely avoids the problems of inheritance. Well, one thing that I'm going to bring now is that C++ is quite unique because it has this weird property that you can use some features to beat in performance and practicality and ease of work some other features of the language, okay? And this thing happens without having to apply any magical stuff. It is just user code. And this does happen in practice. There are multiple examples of this. And in particular, any good type erasure framework ought to be objectively superior to inheritance and virtual. And I will tell you why when the time arrives in this presentation. And in particular, the style of runtime polymorphism that Ross traits give Ross programmers ought to be within our reach. We ought to be able to represent that. And we have done it, and I will persuade you that we can. So we're going to use only one example because I believe that is representative of the problems and representative of the needs for subtyping that are what will allow us to drive the explanation forward. And it is serialization. So serialization, of course, is to dump the state of an object to a buffer so that you can reconstruct the state of that object later by applying the opposite operation of deserialization, right? But we're only going to focus on the serialization part because that's the one that is runtime polymorphic, meaning that if something is serializable, you expect to be able to substitute into an algorithm of serialization and get the buffer of bytes that represent the state of that object. The problem with deserialization is that it is not very relevant to this presentation because that is a factory design pattern. And so it is like, why are we going to talk about that when we are going to focus on the part of subtyping for runtime polymorphism. Okay, so at this point, I should ask if anybody has a question. I really want to give the audience the freedom to ask questions because it is very valuable for you to be live. And when we presenters get questions and comments even, we get some feedback that otherwise we wouldn't get, okay? So please feel free to ask questions during the presentation. It doesn't bother me at all. And if it is a little disruptive, we had to put up with it because it is the way to maximize the value of being live at an audience. And I thank you again for the opportunity to talk to you. Okay. So I hope that this is a very trite example that is not going to confuse anybody. I put in really big font the structure of iSerialize to represent the interface for serialization. And for the purposes of illustrating some things, I could have done only one function, but I chose to put two functions in it. The function that does the serialization by dumping the state into an output stream, and the length that is going to tell you what is the number of bytes that dumping the state of an object would require, okay? I don't even put the comments because it is so clear that it's not necessary, right? Now, because I know that important types in the language, such as, for example, the primitive ones, like integers, double floating points, etc. Even string, for example, don't have, you cannot make them, you cannot force them to inherit from the interface of serialization. I know that for all of those types that I don't control, from libraries that I didn't write, from the standard library, from primitives, I need to be wrapping things around. So I'm just going to create the template alongside with the definition of the interface because the template to wrap things that I cannot inherit is going to be needed anyway, right? And that is what I call serialized wrapper. And if you see the the implementation, I believe that in the slide where I forgot the constructor, but the constructor is trivial to implement. And the implementation of the functions are really not important because all we want is to work with whether something is serializable or not and activate the right behavior, whatever that is. So that's not relevant, but in the interest of some completeness, these things have some implementations. Okay, and again, this is the so-called interface, the thing that we're gonna have runtime polymorphic behaviors that we're gonna require for the serializable things. And this is the wrapper, again, without the constructor. That's an omission that might matter, but it's not really important. So what is it that we can see here? We already saw a problem, which is primitive types such as integer or types that are not primitive but are not ours to play with, like for example a standard string, cannot inherit from this interface, the iSerialize interface. One must wrap them. That's why we do serialize wrapper. Now, let's say that you have your own type and you make it so that it inherits from the interface for serialization. Then you open yourself to two types of problems, or many more than two types, but at least two that I want to talk about because Rust traits don't exhibit that issue. Number one is another application wants its own serialization mechanism that is not the same as the one that you have. And so what are you going to do at that point? Probably you're going to have to wrap your own type using the wrapper for the other way of doing serialization, right? So having made your own type inheriting from the serialization interface was no good at the end. You didn't accomplish anything. And the same problem happens if you want your type to participate in any other subtyping relation implemented as subclassing. So it doesn't scale, it's brittle, unstable. And I do like that Rust traits don't have those problems. So this is, I guess, the time to show you what a trait in Rust looks like. I must tell you that I am not a Rust programmer, but that doesn't mean that I cannot operate with Rust code. And it's very simple. In this example, I am making the serialization runtime polymorphism thingy that I'm telling you about of only one function. So you can call the function serialize on anything that is marked as of the trait serialize. And I define the user type, let's call it point, there is two floating points inside of it. And immediately I show you how to tell the Rust system what to do when serialization is requested from that user type point. And so the implementation for serialize for point is that function and the invocation of the right function on the x and y coordinates of the internal members of the point, right? Now, the last part of the slide is something that in principle we cannot do for C++, which is, let's say that I have a primitive type like integer of 32 bits. We have that type in C++, but we cannot just say, hey, I want the integer of 32 types to be able to participate in polymorphism, runtime polymorphism, for the purpose of serialization and do that serialization in this way. No. I cannot do that. I need to go the circumlocution of wrapping it in a wrapper, and that wrapper is the one that has the capability of runtime polymorphism via subclassing, right? I believe that that's unacceptable because it is pretty much busy work. So what are Rust traits in the end? They are an opt-in mechanism for types to participate in subtyping relations. They are not related to inheritance. I know that I am being redundant, but that's like a truly important attribute, so I'm going to be redundant. And inheritance, again, is a structural property in C++, in architectural decision. And it does not need base classes, so that's not a concern. There are more things related to Rust rates in compilation time, but of course, we're focusing on the part of runtime polymorphism so that they are out of scope, aspects like trait bounds and generics, of course. Who is aware of the concept of dog typing in Python? About half of the audience. Rust rates are similar to Python's dog type concept, just that you need to do something to provide a binding between the interfaces and the objects that are going to be participating in runtime polymorphism. Sometimes you can do what is called a blanket implementation of a trait, in which if the object satisfies certain properties, then you already have the implementation of the trait, and you don't have to do extra work, but technically you still have to do the binding. But again, that is a very strong indication of the opt-in mechanism that this thing has. All right. So the one thing that I want to emphasize about subclassing is that it is an intrusive mechanism. We need to wrap perfectly good types to put them in a hierarchy. This is also like in the number 2 of the top level. This is a feature of the language that you cannot shape with finer granularity for your own purposes. It is a take it or leave it kind of thing. And it's problematic because sometimes you want to play a little bit with how that is implemented. Okay. And then there is another world of hurt. I think that Nikolai Josutis went over some of the insufficiencies of runtime polymorphism based on subclassing. And there is another super duper great presentation that I always recommend people to watch, which is Sean Parent's Inheritance is the Base Class of Evil. So again, anybody who hasn't watched this presentation, please avail yourself from it. It's only 24 minutes, and the part that covers runtime polymorphism is not even 15. And it's great because it is the one presentation that everybody has watched, and the one that we always refer to when we talk about the problem among ourselves. And so you can acquire the language to join the conversation if you do watch this presentation. All right. So the thing is that there is a design pattern whose name is external polymorphism. An external polymorphism allows us to empower any type whatsoever to have runtime polymorphism. So if we also have runtime polymorphism via external polymorphism of the APIs needed for ownership, in particular destruction, moving, copying perhaps, then we have complete control on the runtime polymorphism of the objects. And at that point, we can do something more radical that I call, the type erasure is the thing that is more radical. And for me, the definition of type erasure, the most operational definition of type erasure is when you do external polymorphism on the ownership of the types or instances of the type. So in previous presentations, I have raised the apparent contradiction that type erasure is something very fruitful because it is like a contradiction in terms. It is somewhat of an internal external polymorphism because all of the mechanisms for external polymorphism are internalized, literally. So that's something that's truly important. Of course, that the subject matter of this presentation does not require us to dive very deep in what external polymorphism is, but should you care, should you want it, the best explanation for what external polymorphism is resides in the book C++ Modern Design, C++ Software Design by Klaus Eagelsberger, who is a really loved member of the C++ on C community. This is the cover of his book, and the whole book is phenomenally great. I have adapted my explanations and even the code to refer to things in the way that this book refers to them. So that's how much I care about this book. Now, what is it that we're going to be doing? We're going to be using the extraordinary capabilities of C++ for compile-time polymorphism to translate them to runtime polymorphism. Now, basically, it seems that all you need to do is to have the normal mechanism for runtime polymorphism in the standard language itself, the feature of inheritance and virtual that relies on a virtual table, as you know. So we need to have a way to build virtual tables on our own, because the way to build virtual tables by the compiler is strictly bound to the inheritance and override mechanisms in the language. So that's not going to help us much. But perhaps we can have some metaprogramming templates that will let us assemble virtual tables and use them, right? So that's going to be the essence of one of the most important parts for the purposes of accomplishing what we said to accomplish. And external polymorphism, if you remove this thing of the virtual table and so on, or if you keep it aside, it just looks like a decorator or an adapter design pattern. And you can use other design patterns, including strategy, but that, again, external polymorphism is a little bit for your information, more than needed for this presentation. And then there is a framework, which is the type erasure framework, that is uncompromising about performance, and is rather overwhelming to use because it has so many customization options that people get distracted because of them, and their presence it requires the code to be very, very careful about everything it does so that the customization option can work reliably. And understanding, my collaborators and I, that this is hindering the people from benefiting from this, we want to share with the community something that is easier to use. And we have decided to call it the auditable re-encoding of the type erasure framework. So it's basically something that's going to be in the SU T namespace. We're going to be using it if our proposal for cplusplus that is coming is accepted. Then by that time that I present at CPPCon, it will be completed. And again, the really important part is that it's auditable, meaning that not only it is easy to read, but that you can see that it doesn't do anything prohibited or suspicious or that might raise your levels of anxiety, which is something that unfortunately happens today. But yeah, so let us know if you want to collaborate. And this is what we're going to use for supporting traits in the rest of the presentation. Okay. So again, what is it that we need to do to support cross traits? We need to hold objects of arbitrary types. We need to have control of them, the ownership of them, right? For that is what we need type erasure for. And then we need to bind the function and implementations to the type erasure containers. And that is divided into different tasks. Producing the virtual tables, implementing the virtual tables, and then binding those implementations to the user interfaces that we're going to have. And I mean, programmer user interfaces, APIs. And a third thing that is far less important and we don't have the opportunity to cover today is how to make it feel more Rust-like, okay, more rusty. Like what I'm going to show you is, unfortunately, is just how to use things in C++ that accomplish what the support for Rust traits needs. But it doesn't give you the feel that you are doing Rust traits, even though you are. Okay, and now let's focus on the dynamic dispatch. We will use the virtual table mechanism. An object that is of a type serializable will have a virtual table with pointers to the implementations of the functions for serialize and length. So a virtual table, again, remember, it doesn't have functions. It has pointers to functions, right? And that's important to note because it's an escalating direction, but be as it may, you'll have 2 pointers to functions. But that's not the only thing we need because we also had to have ownership. So we had destruction, moving, and potentially copying. And then these runtime polymorphic behaviors will be activated by invoking the function pointers in the virtual table given the user interface binding that I'm going to describe momentarily. The objects must have all of their state, like an integer has had to have all the bits for representing the value of the integer, and also pointed to the virtual table, like in the case of inheritance with virtual. And the part of ownership is already taken care of by the part of type erasure. Okay, so to make the virtual table, this is something that is a production strength for at least 5 years now. You can see that the Git blame of these lines is very old. And I have slides with that, which is this part. There is a parameter, a template parameter, which are the affordance specifications that is the runtime polymorphic interfaces that the users want to add, okay? And from the affordance specifications, there is a member called VTable entry that get put together into a complete VTable, which is the VTable in the slide, okay? By the way, I believe that this very line is the best idea that I ever had in my career so far. And so this is the entirety of how it looks like to bind all of the work that you need to do to have a runtime polymorphism that is not related on inheritance, like in the style of a Rust trait for serialization, but expressed using the SU type erasure framework. And of course, this is very small. It's here just for completeness, but we're gonna go over its parts, all right? So don't despair, and you will see hopefully that the individual parts make sense. So how does the SU type erasure framework builds virtual tables? Well, we first need to define what are the virtual tables, right? And the virtual tables are defined by pieces. Each affordance, each group of runtime polymorphic functions are grouped together in the part VTable entry of an affordance. If you see, I don't know if you're able to read, but the very first line is a struct serialize affordance. So this is used as sort of a namespace for the purposes of the different parts. And one of the parts is the VTable entry. And the VTable entry, here it says that ugly syntax means it begins with a pointer to a function that takes an upstream reference and a const void pointer. And there is another function pointer called length implementation that only takes a const void pointer. I will tell you momentarily what those void pointers mean by telling you that is the virtual table declaration, if you will, the function pointers that we need, okay? And now we had to concentrate on how to produce those virtual pointers, right? And to produce those virtual pointers, we need the framework is going to give us a concrete, something that I call the concrete value manager, which is the thing that knows what it is managing, that has that knowledge. And because void pointers is the most pointer interconvertible thing in the language, we had to start with a void pointer or a const void pointer depending on the interfaces. And what we had to do is to refine that to what we know is pointed to. Because in this case, if a concrete value manager is my template parameter, then I know that what I have referred to via the void pointer is that concrete value manager. So I downcast it or refine it. And eventually, I have that the concrete value manager can tell me what is the managed type. Let's say, for example, an integer. And it is also going to give me the address of the integer that it is managing. So I can use them, and then I am going to invoke the implementation of how to serialize with the upstream parameter 2, and whatever it is being managed has the referencing of the value pointer. And the case of the length of the serialization is on purpose implemented using the knowledge of the other member. And if you remember, the function pointer is called serialized implementation. And what I'm doing here is to invoke serialized implementation with the arguments given. It is just that I'm substituting, instead of a normal stream references, I am using a local temporary output string stream. All right. So that is the flavor of how to implement the virtual tables. At this point, we have runtime polymorphism because remember, we have the virtual table and the implementations of the virtual table, right? Now, how are we going to bind something that has a user interface that allows me to access that virtual pointer, right? That virtual table. That's what we're going to see right away. So that is the part of user affordance of the affordance. This is what is added to the user interface. And I'm calling the member function that I'm going to be adding to the user interface set, just to not use the word serializing all the time. And what I am explaining in the code via the naming of the identifiers is that the user interface containers, the top level thing that will have that we are going to add the function ser, is a curiously recurrent template pattern based of the part user affordance of the whole affordance specification. Have you ever heard the curiously recurrent template pattern? All right, that's I see that about 1/3 of the audience doesn't know what is the curiously recurrent template pattern. Please come to me that I can explain it to you. But this is a way to refine, to give powers to derived classes by adding a base class to them. And what we're doing is to access that base class that gives us the extra powers. And now, because we know that we are using a user interface container that it has a user affordance bit to it, we can tell it, okay, I know that you have a container, so give me the container, and that will be the pointer to the base value manager. So all of the concrete value managers are derived classes of the base value manager, and the base value managers give me access to the virtual table, that thing that we built in the previous slides. And in that virtual table, I know that there is a member which is a serialized implementation, which is a function pointer, and I can invoke that function pointer in the line that you see here, right? And that's how we bind the user affordance. Okay, so far we have been presenting to you guys what the infrastructure programmer does to implement the ROS trait of serialization for users to use. But we have not seen how the users uses it. And this is exactly how. So in the first few lines, we're going to set a policy type for the purposes of subtype erasure. That the first few lines, the void pointer means manage everything on the heap. Don't care about using the local storage. And I want to use the normal runtime polymorphic behavior of normal destruction, because you can use some other forms of controlling the destruction of objects. But in this case, it's just the stock, the normal destruction, the normal moving, the normal copying. Therefore, the objects that this thing manages need to be copyable and will be copied on the cases that copy this, what ought to happen. But this is a choice. You cannot. You are able to not use subcopy, and then it will be move only. And look, we are using serialized affordance, which is the top level thing that put all of the other components together that I showed you a moment ago, right? And to use the serialized trait, you're going to get something that is of type serializable, which is a sub any container on that policy. And you can invoke the member ser on serializable, and that's what it's going to activate in the way that I described before, the behavior that is runtime polymorphic. And the function that will transform an integer into a serializable is what ends the slide. It is simply to return it. Of course, that it begins as an integer type, and now it is of a different type, which is a serializable, which is a any container on the policy that has the affordance of serialized affordance. Questions? All right. So, of course, we can see this live in the compiler explorer. The compiler explorer has a couple of things that are done for the purposes of explaining this in a presentation. Number one, I am mocking STD, and the idea of mocking STD is to not get distracted with the actual implementations of OStream and OStream. So if you see here, I just declared the templates and pretend that they live in a different translation unit. And that simplifies enormously to understand the assembler. And what I'm going to show you is how it looks like when first, when we use the serialized wrapper for an integer. So you see here, for example, by the way, are you able to read the source code in the left side of the compiler explorer? All good? Yes, all good. To make a serializable integer, I cannot return something that has value semantics, which is a big drawback on its own. And I just say, well, I'm just going to return a pointer to something initialized on the heap that is the wrapper for the integer, okay? Nothing so more complicated than that. Now it is the time to do this font much larger. I hope that you're able to read it. And that is all the assembler for building, make serializable, for building and allocating an integer. And to use a serializable, an interface serializable thing in normal runtime polymorphism, I call that a function serialize iSerializable. Sorry that this is becoming somewhat of a tongue twister for me, but be as it may, this is how the assembler becomes for the purposes of serializing an iSerializable. And of course, what is happening here is to determine the pointer to the entry in the virtual table to the thing that actually does the serialization and invoking it with a jump at the end. And of course, there is an implementation. We can see in this assembler the implementation, but I think that is not necessary because it takes time and we can move on. And well, this is making one and using one, right? And look at, this is the serialized affordance that I showed you before, but has runnable code. This is the part of serialized affordance, : VTable entry, serialized affordance, : VTable entry operation. The default is in the case that the container is default initialized, so it doesn't have something in it. So this is something that you have to think about what ought to be the behavior, but in general, this doesn't happen in the normal execution. This is like a border case that you have full freedom of what to do with it. The user affordance part, you see, it is the member ser, and I don't know, like this compiles, of course, and if the internet works, I can. Oh, that's not what I meant. We are very close to ending the presentation because we are arriving to. So this is going to fail to compile because, of course, that I changed an important name. And so that's what tells you. See, I have a serializable type, and that is the thing that adds what I wanted to illustrate with this change is how the part of user affordance adds to the user interface of a SUNY container. Okay, and see that it is far more economical on the assembler. This is the part of how to use what we really care about, right? Polymorphically invoke behaviors, or invoke behaviors that are polymorphic in nature, runtime polymorphic in nature. In the case of interface serializable, and in the case of rostrate, you can see that the assembler is much more economical. And this is all that it needs to do to create serializable, has rostrate or rostrate equivalent, and see that it basically only takes care of putting the virtual table pointer has the first member and then copies the integer. And this is, if you care to see, this is the virtual table. Sorry. This is the virtual table. This is what it is pointed to, okay? And see that there is a function that is initialized to the address of by value of an integer. That is by value is the concrete value manager. Integer is what is being managed, the destructor, and the moving, the copy operation, a lambda for the purposes of the serialization indeed, and this is the lambda of. So you can see that this is the complete virtual table. This is something that you can play with, of course. You're going to have these slides later today on the Discord. If we come back from planet Earth, we can say that this all looks like awful code, very ugly code. But I hope that you appreciate that it is also very repetitive. It is boilerplate. It's basically converting the void pointer to the concrete value manager and using the architecture of the value managers to find the value, the type that is being managed, and so on, right? I know that's the work that I'm doing, that we can de-emphasize the customizations we don't strictly need to encapsulate the most common uses and get something that allows us to express it very succinctly. The really hard problem that we run into is that this is all driven by identifiers. And as of right now, C++ doesn't have any real way to deal with identifiers in code. That presents us with a pick your poison choice. And the primary two poisons that we are allowed to choose are to use reflection proposals ahead of time or to use preprocessing. And I have done preprocessing for these things for some organizations that use this code. I know that it works. I know that it's a practical solution, but it is preprocessing, and preprocessing is always an asterisk that I would rather remove than leave there. But I want to emphasize that this is all we need. We have all we need to support rostrates. So I have delivered on the premise of the presentation, because we have the virtual table to have dynamic dispatch. We have how to implement the functions that will be referred to by the virtual table. We have the binding between the real objects and the virtual table. We know how to add them to the public interface. And we also have destruction and moving taken care of, right? So we have the complete set of capabilities to support rostrates. And we saw that the performance is great. So, or the assembler indicates that that's probably optimal code, which is even a stronger claim. We do the same things that rostrates do. We do subtyping without subclassing. This is opt-in. Basically, what we did is to use how to serialize implementation for T, invoking such a function. And that's going to work if the thingy is able to be inserted in an output stream. And Rust allows you to do this thing. So we're not getting ahead yet in C++ to what Rust allows you to do. And this would be the way to do a so-called blanket implementation. In this particular case, everything that implements display is going to be able to be serializable. That's what this slide means. And so what's lacking? That we need to solve the problem of the identifiers, right? So let's talk about a conclusion. We have arrived to the end of the presentation. So we can capture runtime polymorphism in the style of Rust traits. This is something that was illustrated with actually running code, which is opt-in subtyping without inheritance or subclassing. But I didn't tell you, this is probably not for the conclusion, but this is the time, I guess, to tell you that we have advantages. Because that any container gives you something that Rust traits don't give you, which is value semantics. In Rust, if you want to keep the nature of runtime polymorphic thing, like you're not going to use a concrete type that happens to be serializable, but you want to have something that is serializable so that at runtime it can be filled with whatever is serializable, it will continue to be runtime polymorphic, and then it will almost always almost leave behind a pointer. There are resources like box, array, dynamic trait, arc, etc. And all of them have referential semantics, not value semantics. But subtype erasure already by stock gives you value semantics that you can use. You have the choice to use it and never downgrade the quality of your code to referential semantics. Furthermore, you have much more capabilities. In particular, you can configure the size of the local buffer for your purposes so that it is a large local buffer or for a very large alignment like a cache line alignment, so that the thing has to punt to having to allocate on the heap far less often. And therefore you get massive gains in performance, as many of the users of this framework have reported. So the real conclusion is that C++ is that powerful. Thank you very much for your attention. It's been a pleasure to talk to you.